Welcome to Revolution Against Evolution. I'm your host, Doug Sharp.
Your co-host, Rich Gear, with you as well. And we have an exciting show for you today, talking about Dr. Raymond Damadian, the inventor of the magnetic resonance MRI, basically, which is used everywhere. We had a great trip out to New York, and I don't know, Doug, you want to share a couple of your thoughts? There's so much to share, but I'm going to let you go in on this because it's up your alley, really. You're the chemistry guy.
Well, we're about to go into the second half of this interview that we did with Dr. Damadian.
Right.
And in this interview, he is explaining the cancer research that he was doing back in the 1960s and 70s.
Yes.
Where he was trying to figure out what was really the cause of cancer and how he could detect cancer in the human body.
That's what's so exciting.
And we're just getting into the portion of this interview. If you haven't viewed the first interview before, that's on our website. Check that out. But this is the second half of it. And he's about to explain to you the breakthrough that he had in terms of the experiments that led up to the invention of the MRI.
Dr. Cope calls me up, says, let's look at your theory, Damadian. So I said, Cope, so what do you want to do? He said, well, I know of a small company on the outskirts of Pittsburgh called NMR Specialties, and they have this technology, but they have a special kind of NMR machine. The present NMR machine that everybody's using, Damadian, does chemistry and does spectroscopy. So what you end up, what the chemist does is he takes this test tube, puts it on the inside of the magnet, and then he looks at the frequencies of the different atoms that are inside the test tube, and then he maps it, and that's a spectra. Mm-hmm. I'm suggesting something completely different, Damadian. We won't look at the frequencies. We will look at the signal itself and see how long that signal lasts.
Okay.
And if you're right, Damadian, and if your argument that the potassium is accumulating by sticking the negative ions, that should affect the decay time of that signal. That should affect the relaxation time of that signal, which is another name for the decay time. Mm-hmm. If you're right, Damadian. So I said, Cole, well, what do you have in mind? He said, well, we'll measure the decay time of the signal from potassium in liquid water, and we'll measure the decay time, the same decay time of the potassium when it's inside some tissue. And if you're right, Damadian, that decay time should change markedly. If you're right, Damadian. And the way we can prove it is we just put it in this special NMR that allows us to measure the decay time of that atomic broadcast. Okay, it sounds good, Cole. What do you want to do? He says, well, right away. He says, oh, okay. And he says, I got a lab in New Kensington, Pennsylvania that will do it. We'll cooperate with us. Same place I bought my machine, but it allows us to measure the decay time. It's not good. I said, all right, let's go. Let's set up to do it, Cope. So he calls back in about a week. He says, I'm worried, Damadian. So, well, Cope, what do you mean you're worried? He said, well, I looked into the magnetic moment, how strong the magnetic moment of that potassium atom is, and it's not very strong. And I also looked into how much potassium is on the inside of the tissue to see if I can get enough signal. My problem, Damadian, is I'm afraid we're not going to be able to get enough signal. There isn't that, the potassium atom doesn't have that strong a magnetic field to begin with, and the amount on the inside of the tissue isn't all that great, and I'm afraid it's not going to work. So I said, wait a minute, Cope, I have an idea that I may be able to help. I said, what are you talking about, Damadian? I said, I know of a bacteria from the Dead Sea that has 20 times the normal potassium. It's called Halobacter halobium. I read about it in the books.
Say that 3 times real fast.
He says, do you think you can get it? I said, I don't know, Cope. I'll hang up and I'll start calling around, see if I can get hold of this bacteria. He says, good. Call me back and tell me if you're able to get it. So I called around a number of different places, and I was able to locate a source of this Halobacter halobium that had 20 times the amount of potassium of an ordinary cell. Says, oh, okay, all right, mate, let's go out to New Kensington to this company that has this pulsed NMR called NMR Specialties. You bring your bacteria. I know of a laboratory there where you can go and grow up the bacteria, and I'll run the machine. So I get the bacteria, and I go out, and the professor colleague of mine, Stanley Schultz, was also at the in New York. Schultz can I use your lab to grow up my bacteria with my big vats? He said, yeah, sure. So I grow up the bacteria in these big 20-gallon vats, and I spin it down a test tube, and then I travel over in a car to NMR Specialties, and I give the test tube to Cope. So Cope says, okay, Damadian, takes the tote, takes this test tube with the halobacter with 20 times the normal potassium, puts it inside the magnet with a coil around it, and instantly measures the potassium, and measures decay time, and shows that the decay time is much shorter. I said, Cope, I can't believe what you just did. He said, what are you talking about, Damadian? I said, listen, Cope, I've been measuring this potassium for several years, and I have to go through an elaborate wet chemical analysis method, and if I don't drop the test tube, and here I give it to you in a matter of 3 seconds with non-invasive electronics, you make the same measurement that it takes me days to do. I said, Cope, I can't believe what you just did. I said, Cope, do you realize that if we could ever do that on the live human body, we would be able to go from one tissue to the next and get its chemistry without ever invading anything? No, because here I am talking about a magnet that's 2 1/4 inches in diameter, and I'm dreaming about putting a human body in there, which was going to be absurd. So I says, no, Cope, Cope says to me, he says, I don't even know where you would start. I said, well, I got an idea on that one, Cope. What are you talking about? I'll do it on cancer, Cope. What's in your mind? I said, well, from everything I've read on the iron composition of cancer tissue, I know that the iron content and the iron composition of cancer tissue is abnormal. And if it's abnormal, the signal ought to be abnormal. We should do it on the water signal, because I'm expecting that the potassium and sodium is going to be abnormal, so the water signal should be abnormal, and we should get an abnormal water NMR signal from cancer tissue as compared to healthy tissue. So I was wanting Cope to collaborate with me. Well, he thought it was off the wall. He really didn't want to go forward and do it. So I went to the president of the company, Paul Yako, and I said, listen, I have this idea. Maybe, if it's kind of a wild idea, but I said, if at least we can show the signals different between cancer tissue and normal tissue, we can talk about building a scanner for the human body. So Yako says, fine, come back when you're ready.
And what time period are we talking about right now? What year was this?
Well, the original proposal I had was 1969.
1969,
Okay? So it says, fine, come on back, go home, get your animals, whatever you want to do, and bring them back, and I'll let you use the scanner under one condition. You don't use any of my personnel to run the scanner. You got to do it on your own while you're here. And Cope had done all the measurements, so I didn't even know where to start, which buttons to press, okay? So I get back there, and he hands me the spectrometer and a test tube and a magnet. And he hands me the manual. This is the operator's manual, Damadian. So I said, all right. So I start measuring on liquid samples and test tubes and so on and so forth. And I do several weeks worth of work, and finally get to the point where I can trust the numbers I'm getting, and I'm getting reliable numbers. So I said, okay, the big moment. And I had some rats with me that had cancers in them, and so I cut the tumors out, put them in a test tube, put them in a magnet, and did the same thing with the healthy tissue. And I measured the decay time of this signal. And the decay time of the cancer tissue was dramatically different than the decay time of the healthy tissue. It was much longer. So I said, holy smokes, it's actually working.
It actually works.
The signal from cancer tissue is dramatically different. This is something that we could potentially non-invasively scan.
And were you still doing this on the little...
Doing it on a little test tube.
Little test tube, okay.
I cut the tumors out, put it in a test tube, put a test tube in.
Little tiny little thing, okay, all right.
So, because it was such a dramatic result, we published it in this world famous journal, Science, and it appeared in print in 1971. And the other thing that was stimulating our interest in is at the exact same time, President Nixon had announced that he's going to commission a war on cancer, and he's going to provide $1 billion a year in research funds to people to overcome the disease of cancer, which of course meant that I was going to have an ample supply of research funds to do this research. I get a phone call from the head of the cancer diagnosis program, Dr. Ken Olson, who had been assigned this responsibility as a professor himself of overseeing the Nixon cancer detection program. And Dr. Olson called us and says, "Damadian, I read your paper in Science." He says, "It's very interesting." He said, "We want to follow up on your research. We want to use the research program that has been put forward by President Nixon to follow up and see how far. First we want to do is validate all the numbers that you got, and then if everything is working, we'll try to proceed to make the scanner that you have in mind for scanning the human body." I said, "Well, that sounds great." He said, "We're going to put out a contract. The contract will provide $100,000 a year, and we'll let everybody compete. And if you win the meeting, you'll get $100,000 for 2 years, $100,000 a year for 2 years. And we're going to have the contract available to 3 research scientists, so everybody can compete, but we'll only select 3. So he says, "Well, go ahead, Damadian, and get started." So I get started. The contract, we compete, and we get the contract, and a group at Baylor University in Texas gets a contract, and a group at Johns Hopkins gets a contract. And then Dr. Olson calls for a convention of all the people who have been working under the Nixon program for cancer diagnosis. And ours was only one segment of this, but he holds a big conference at the National Cancer Institute in Bethesda, Maryland. There's hundreds of scientists come from all over the place. And our section on the NMR, the MRI, is only one small section of this whole collection. So as different scientists start giving their report, it finally comes to the cancer detection, NMR cancer detection, that our 3 scientists are part of. Okay? Says, "All right, Dr. Damadian, I want you to go first. You tell what your results have been." So we get up, and we had now made the measurements on cancer tissue in live mice. And we made some images and pictures, and we were able to see the tumor in the live mouse. Then the next scientist, Dr. Hazelwood, from Baylor University, gets up and he says, "All right, I did the measurements for the past year, and I measured the T1 and the T2 of cancer tissue like Damadian, and I got the same abnormal T1 and T2 that Damadian got from his signal." Now, I should tell you what T1 and T2 is just briefly.
That would be
okay?
good, yeah.
What?
That would be good.
Okay. And it's very simple. As I said, we're collecting from the body a radio signal from the atom. And what we do is we stimulate that atom to give back its own radio signal. So we pump in a radio signal, and then we wait for the signal to come back and pick up on the antenna. And the signal that comes back doesn't last forever. It starts off big, as you would anticipate, and it slowly decays. And what we measure is the decay time. And there are 2 decay times that we measure, and they have names. The T1 decay time and the T2 decay time. The T1 is called the spin lattice relaxation time, and the T2 is called a spin-spin decay time, but there are 2 decay times. And we measure them, and they're different, okay? So this, I'm able to give my report and say that we've been able to measure this in the live mouse, and we got the same abnormal T1 and T2 in the decay time from the live mouse that we got in our test tube samples. And Dr. Hazelwood gets up and says he had measured the T1 and T2, and he got the same delayed T1s and T2s, the longer decay times that Damadian got. Then the 3rd professor from Johns Hopkins University, Dr. Hollis, gets up and he gives his presentation, and he said, "Okay, I measured the same decay time of T1 and T2 that Damadian measured in cancer tissue, and I got the same delayed decay time that Damadian got in cancer tissue."
So this is 3.
Huh?
This is 3 different. You and 2 other people have gotten the same results.
But I'm not done yet.
Okay. I'm just making sure I'm following you clearly. You know.
All right. So the 3rd doctor who has done the research, Dr. Hollis, said, I measured the T1 and T2 of cancer tissue and compared it to the decay time of normal tissue, and I got the same abnormal decay time that Damadian did for cancer tissue. But
Okay.
I measured the same signal from diseased tissue that was not cancerous. And I got the same decay time that I got for the cancer tissue. Therefore, ladies and gentlemen, any further discussion about scanning the human body by NMR is visionary nonsense.
Oh boy.
Because you can't distinguish cancer tissue from other disease tissue.
But they're cancer's disease tissue as well as others. I mean, so is the difference between both the disease, which is not cancerous, and cancer cells, is that different from healthy cells?
Well, you're asking the key question.
That's
Okay.
okay. All right.
No, but because that became a central issue, and we ended up after all this was done, we ended up in a big patent fight with General Electric. Okay.
Oh.
And General Electric made the same argument. General Electric said, "Wait a minute. You got an abnormal signal for a cancer tissue, a delayed decay of cancer tissue, but you get the same abnormal signal from other disease tissue." And the response is, yeah, but you got delayed signal, an abnormal decay in two disease tissues that were different, both of them were different from the normal.
Yeah.
And our attorney said, now wait a minute, GE has argued that you got an elevated signal from cancer tissue and the same elevated signal from other disease tissue. Ladies and gentlemen of the jury, you're going to punish the guy because his original discovery detects more disease than he originally imagined?
That's what I was getting. Yeah.
Yes, there you go.
So gratefully, we won. The jury found in our favor, and the judges upheld it. And then the other amusing aspect of this is that after we won, the award was $129 million.
Yeah.
And the head of the jury came up to me on the decision, and it said, she said to me, if it hadn't been for the men on the jury, your award would have been $400 million.
Now,
The ladies wanted to give you $400 million.
at this point in time, had you come up with a full-size body scanning thing yet? Was this before or after?
Yeah, no, let's see now. When did this, yeah.
The lawsuit was about weren't they
No,
ripping
no. We had built Indomitable.
Yeah.
And we had by this time we had a full-size body. We had Indomitable.
Let's talk about Indomitable
We
a
had
little
done the
bit.
first scan, but
okay.
Just let me just finish this point. So
Okay.
after we get that decision, I get a phone call from the CEO of General Electric.
Jack Welch.
I get a phone call from Jack Welch.
Yeah. Big dude.
And Jack says, Dr. May, this is a phone call I should have made a long time ago. He said, but I want to talk to you about reaching a settlement on this patent dispute between your company, Foner, and GE. So he says, I'd like to come and meet with you. He says, I'll come to Foner Incorporated with me. I said, no, wait a minute. Dr. Welch, that makes me a little nervous. I said, I don't want to meet with you without my lawyers present because I don't want to end up saying something that's wrong that's going to end up fouling this all up.
Exactly.
So he said, okay. Where do you want to come? I said, well, if you don't mind, when I have my lawyers, I said, we can come to your main offices in Manhattan. He said, oh, okay, fine, man, come to the office in Manhattan. So we go to the offices. I go there with my two lawyers, and with Jack Welch and me. And we had sued them on two patents. We had sued them on my original patent, which was the discovery of the T1 and T2, and we had sued them on another discovery that we made, where we were allowed to, we came up with a technology that allowed us to make the cuts, the slices of the MRI at different angles. An oblique would make slices. So we had, and they were using both of them. So we sued them for patent infringement on both those patents of our company. So Jack Welch says, okay, Damadian, he says, I'm ready to go ahead with a settlement, and what I'm going to propose is that I'm ready to write a check right now for $80 million. The award had been for $129 million. He said, but we're going to take your original patent, the first one, the 832 patent, we're going to set it aside. We'll pay you on the second patent. I said, well, but that's tough on me, Mr. Welch. I said, because that's a hard one on my soul. That's my heart and soul. And you're just setting it aside as though it's an insignificant event.
Because that T1, T2, that's the primary discovery.
Oh, the T1s and T2s,
Yeah,
that's
the
right.
primary
And
thing.
you're just setting it aside as though it's irrelevant. I said, that's a hard. Well, as I'm doing that, the faces of my two attorneys are turning very grim because they had taken the case on full gratuity. Namely, if we didn't win, they didn't get anything. If they did win, they got $40 million. They got 40%.
32 million.
So that would be $50 million. 40% of $129 million is almost $50 million. So the legal fees that they were going to get was $50 million, and I just turned it down. I said I can't.
I thought when I was reading your book, maybe I got this wrong, but I thought in the book, I remember reading that he was going to write you a check for $80 million.
That's right.
Instead of the full $129 million.
Oh no, there was no.
Yeah,
it was $80 million.
Yeah.
It was $80 million instead of $129 million.
That's what I'm saying. Yeah, and they would have got 40% of that.
They would have gotten 40% of the $80 million. I said the wrong thing.
Yeah, that's what I was
They
getting
would have
at.
gotten $32 million.
Yeah, that's what I said. Okay.
Yeah.
Yeah.
They would have gotten $32 million.
It was still a lot of money.
And
they were going to lose out on.
And I was turning down their $32 million.
But it's interesting because when we read the book, what was the reasoning that you had for turning that down? I mean, $80 million is a lot of money to walk away from. You know, I know that there's a thing there, but it's like there was something in you as a person that would not settle for that for a good reason. And I love the way you put it in your book. And there's something about truth, about integrity. There's some things about it you're talking about that.
No, I wouldn't say it was integrity so much as what they were doing is disqualifying my discovery.
Yeah.
In other words, they were saying my discovery is of no consequence.
And that wasn't true. That wasn't real.
No.
Yeah.
I mean, the whole industry was running off my discovery, and they were disqualifying the discovery.
Right.
And that was painful for me, because I'd given my life to that discovery, and they're just shoving it aside. And anybody would be in a position thereafter to say that the discovery was of no consequence.
Right.
So that was very painful for me. But it was even more painful for my attorneys.
So then you actually did go into the court, and you still won.
No. So what then happened was, we're going to take it to the Supreme Court, because that's what he said. If you don't settle for this, G's going to take it to the Supreme Court. So he sent it to the Supreme Court. At that point in time, just by coincidence and timing, I had been invited to make a presentation of this new MRI NMR technology to the armed forces. Specifically, I was invited to the United States Air Force, a big convention, the United States Air Force. They wanted me to present to all their Air Force scientists this discovery of T1 and T2. So I'm down there in their headquarters, and there's probably a dozen Air Force generals that they asked me to come and speak to, and I'm down there with our executive, Lou Banani, who's our executive vice president. I phone her. And while I'm talking to the generals, suddenly somebody comes in from the outside, and Lou Banani comes in and says, "Dr. Main, you got a phone call from your lawyers on the General Electric case, and they want to talk to you." So I said to the generals, I said, "If you don't mind," I said, "we have this case that's been pending against General Electric. It has gone up to the Supreme Court, and my lawyers need to talk to me." So I go over to pick up the phone, and Lou Banani's standing there with me. And my lawyer says to me, "Well, Damadian, you don't know this yet. What do you?" He said, "We just got the decision from the U.S. Supreme Court, from Judge Rehnquist to GE. The decision is GE, pay Foner, pay him now."
Yeah.
Oh, no.
Yeah.
So the two of us start jumping and with our arms around each other, jumping and screaming in ecstasy.
Who
and
else
the judges come running out of the room to see what in the world is going on.
Who else was with you jumping?
Lou Banani.
Okay,
He is our executive vice president.
Now, by this time, you've already had the Indomitable up.
Oh, that's right.
So I'd like to go backward just a little bit and talk about the process of when you come up with what you call an Indomitable. That's why I say this thing with a case, it seems more like almost like your indomitable spirit, or with that thing that the Lord's put in you, just to carry through. But
Which is the very first MRI.
The very first MRI. And there's a lot of stuff that was going on. This is a very interesting and fascinating story.
And at one point in time, that machine was at the Smithsonian.
Is it still there, or is it not there now? Is it
I don't think it's
No,
there.
I think it's not there now. It was big and taking up a lot of space, and they have it all in boxes right now. The latest I've heard on that.
Yeah, we've got a lot more.
But it was there for a while.
Better retrieve it
the
and
question is,
put it back on display here, right?
yeah, no, that's the right thing to do.
So you took this idea, it seems to me, that this little thing inside this little 2 1/4 inch, and then you got this idea you could maybe do a full body thing, and that's where. And by the way, that's where all this court case came from, because there were other people starting to, once you had figured it all out. But what were some of the things that happened? I mean, it's a very fascinating story, because the perseverance to go through this, the keep going on, is a fun story, and you had a lot of associates that were with you along the way. When we tell the story, it's kind of some humorous things there a little bit. When you talked about the time you trying to get it. Well, the first thing is that and I'm jumping around a little bit. You're needed to get a wire to make it or something. And tell us about that a little bit.
Well, the long and short of it, and the reason there was so much ridicule, is that we're talking about taking an analyzer of a 2 1/4 inch test tube and replacing the test tube with the human body.
Yes.
Mm-hmm.
And hey, yeah, we're going to put the human body in that 2 1/4 inch magnet. Well, it's obviously not going to put it in a 2 1/4 inch magnet. Right away, you realize you're going to have to build a much bigger magnet. And then the antenna is going to have to get much bigger, because instead of the antenna going around a 10 millimeter test tube, the antenna is going to have to go around a 20 inch body. Well, everybody thought the whole thing was ridiculous, because when the key to this whole technology was the signal that we talked about initially, the radio signal coming from the atoms. And the big fear that we all had was when we're going ahead and trying to detect a small tumor in the center of the body with an antenna that's 10 inches away, when the normal antenna is 10 millimeters away, that everybody said it was ridiculous, you'd never get enough signal. But anyway, we had now come to the point that it was unequivocal that the signals from cancer tissue were different from normal, and so now if we were going to go forward, we'd take the next step and build a magnet big enough to put a human being in, which was a real tough go, because everybody thought it was absurd.
It's 1977 at Downstate Medical Center in Brooklyn, New York, today known as the State University of New York Health Sciences Center in Brooklyn. Dr. Raymond V. Damadian, then a faculty member, and his 2 graduate assistants, Larry Minkoff and Michael Goldsmith, has spent a year of nearly round-the-clock work in a Stark University laboratory, building a machine that would, they hoped, scan the human body using the principle of nuclear magnetic resonance. Not only something never attempted before, but something never even thought of before. They called the machine Indomitable. For Dr. Damadian, it was an all-out attempt to realize a dream, born out of his work done several years before on the NMR relaxations of normal and malignant tissues. But would Indomitable ever work? This tremendous effort punctuated with frustrations, disappointments, and financial difficulties. Would it ever pay off? It did. At 4:45 a.m. on the morning of July 3rd, 1977, Indomitable produced the world's first MR image, a cross-sectional view of Larry Minkoff's chest. The scan took nearly 5 hours to complete. The MRI industry was born.